Hello again, analysis students. So, this is part 2 of the lecture on Cauchy sequences. Thus far, we've used the Cauchy criterion to prove that a sequence converges, which otherwise would have been difficult to show convergence of. But we didn't actually prove that a sequence is convergent if and only if it's Cauchy. So, this is on a page which is fair enough above. I'm going to write the statement of the theorem off to the side, along with a sketch of what it is that we need to show. So, what was, this button. Theorem 2.8.2 above the Cauchy convergence theorem. It says that a sequence is Cauchy if and only if it converges. And that theorem is totally meaningless if we don't point out what it means for a sequence to be Cauchy, which I'll remind you of right now. A sequence, A sub n, is Cauchy means for all epsilon bigger than 0, there exists a choice of big N such that for all little n bigger than big N, and for all little m bigger than big N, absolute value of a sub n minus a sub m is less than epsilon. So let's do it. So presumably it'll be very easy to show if a sequence is convergent, then a sequence is Cauchy. And in fact, maybe I'll sketch a picture of the proof of the forward direction right here. A picture of convergence implies Cauchy. So by picture, I mean literally I'm going to draw a triangle. So there's a sub n, there's a sub m. I would like the distance between them to be less than epsilon. Right? If I'm trying to show that a thing is Cauchy, then there's the conclusion that I need. Now I know that this sequence is convergent, so if it's convergent, it has a limit. I'll call the limit a. And let's see, as long as little n is big enough, then I can get this distance to be less than epsilon. And this is just a scratch walk kind of thing, so I'm not going to tell you what that big N is, but that big N is the thing that comes from the fact that a sub n converges to a. Similarly, if little m is bigger than big N, then this will be less than epsilon. Oh, but then the triangle inequality will tell me something. The triangle inequality, like the geometric way of saying it, is no edge of the triangle is longer than the sum of the other two edges. So this side is going to be less than 2 epsilon. Oh, but then I know exactly what to do. If I divide this by 2, I divide this by 2, then I'll wind up dividing this by 2, and I'll wind up with epsilon. So this tells me everything that I need to know about the proof. So I'll get my choice of big N using the fact that a sub n is convergent. And I'll use epsilon over 2 instead of epsilon. And then the triangle inequality will finish the proof. So there's a picture of the proof. Let's go over here and actually write the proof. Convergent implies Cauchy. Let's let a sub n be a convergent sequence. Suppose that the limit of a sub n is a. I need to show that for every epsilon there is some big N, such as little m is bigger than big N, little n is bigger than big N, then absolute value of a sub n minus a sub m is less than epsilon. And I got ahead of myself That's exactly the stuff that I set off to the side. So there's the thing that I want to show. I want to show that there is, for every epsilon bigger than 0, there is some big n such that if little m is bigger than big N, little n is bigger than big N, then absolute value of a sub n minus a sub m is less than epsilon. Now, the way this is written even tells you how the proof should go. I need to show something is true for every epsilon bigger than 0. So I'll consider any epsilon bigger than 0. I need to come up with a choice of big N. The next part of the thing I want to show is that there exists some big N such that some stuff happens. And I already know how to pick this big N. Because a sub n converges to a, there is some big N such that if little n is bigger than big N, then the absolute value of a sub n minus a is less than any fixed positive number that I want that doesn't have to do with big N or little n. And I know what I want. I want epsilon over 2. Nice. So we've considered any epsilon bigger than 0. We've gotten our choice of big N. Next, I need to consider I need to show that something is true whenever little m is bigger than big N and little n is bigger than big N. So let's suppose that little m is bigger than big N and little n is bigger than big N. Then, well, because little m is bigger than big N, this inequality holds for little m. So a sub m minus a is less than epsilon over 2. Similarly, because little n is bigger than big N, the absolute value of a sub n minus a is less than epsilon over 2. All right, so because I have those two things, I know I'm going to have to use the triangle inequality because that's how the sketch off to the side went. So let's use the triangle inequality. So the difference between a sub n and a sub m, well, I know that they're both simultaneously close to a, so that tells me that I should subtract and add a. Right, there's always a difference between can and should. You can add and subtract anything you want, but this is the thing that you should. So the difference between a sub n and a sub m in absolute value is the same as the absolute value of a sub n minus a plus a minus a sub m, is less than or equal to absolute value a sub n minus a plus absolute value of a minus a sub m. But I know that this is less than epsilon over 2. I know that this is less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2. That's epsilon. And so let's just read through this conclusion and see if it actually holds. So I claim that this shows that if a sub n converges, I assume that a sub n converged way up there, then for every choice of epsilon, there exists a big N. So there's me coming up with a choice of big N. I didn't have a formula for a sub n, so I knew I couldn't get a formula for big N. I knew a fact about a sub n. I used that fact to get a choice of big N. So if little m and little n are bigger than big N, then absolute value of a sub n minus a sub m is less than epsilon. Nice. So this proves that the sequence a sub n is Cauchy. Let's go the other direction. Let's prove that if the sequence is convergent, then it is Cauchy. And this will be a proof that will seem maybe a little bit more novel. So right now, all I know is that the terms of the sequence get close to each other. I don't even have a name of a thing that should be the limit. So here's what my strategy is going to be. Sketch. First, I'll show that a sub n is bounded. Now, certainly, if I'm trying to show that it converges, and I can't even show that it's bounded, then I'm probably screwed. Every convergent sequence is bounded. There's step one. Because if I can actually show a sub n is bounded, then I'll be able to use the Bolzano-Weierstrass theorem to get a subsequence a sub n sub k, which converges, and let's say it converges to, some number a. Well, if the whole sequence is supposed to converge, then it will only have one choice. Oh, that's interesting. about where it could converge. If the sequence converges and it has a subsequence which converges to A, then the only place where A sub n could converge is A. So I'll show that A sub n converges to A. Once I have a candidate to show that a candidate to be the limit, then I can actually try to just directly show that A sub n converges to A. So there's a sketch of the proof. Let's do it. All right, so boundedness first. So let's suppose that A sub n is Cauchy. I need to find a candidate to be the limit of A sub n. And in a first step towards doing that, I'll show that A sub n is bounded. Now, just like the proof that every convergent sequence is bounded, there will be some big N that there. I'll use a small choice of epsilon. To show that a sequence is bounded is a much lighter conclusion. So I can probably use much less than the full strength of Cauchy. I'll use the Cauchy condition with a fixed choice of epsilon. Epsilon equal to 1 will do the trick. You can rewrite this with epsilon equal to 5 and you'll do fine too. Let epsilon equal to 1. Then, well, let's be totally clear. Because A sub n is Cauchy, and because this number is positive, oh, come now. I know that there exists some big N, such that if little m and little n are both bigger than big N, then the absolute value of A sub n minus A sub m is less than that choice of epsilon, namely 1. So that means that as long as little m and little n are past this threshold value of big N, I have good control over how different they could possibly be. So here's what I'll do. I'll fix m to be a particular thing that's bigger than big N, namely, that's the wrong button. I'll fix little m to be this particular thing that's bigger than big N. Then I'll know that something happens for every little n bigger than big N, because this is, give it that I know this fact for whenever little n is bigger than big N. So I'll know that absolute value of A sub n minus A sub big N plus 1 is less than 1. And I'll go ahead and take this and I'll solve for A sub n. And you know exactly what the end result of this is, and if you don't, then go through it real quick. I won't go through it right now. Solve that for A sub n. I'll get A sub big N plus 1 minus 1 is less than A sub n is less than A sub big N plus 1 plus 1. So that looks an awful lot like A sub n is bounded. That looks an awful lot like this is a lower bound and this is an upper bound. But, well, just like in the proof that every convergent sequence is bounded, this doesn't actually do the trick. This only does it as long as little n is bigger than big N. Big N could be like 10,000. This doesn't say anything about the first 10,000 terms, but how many terms are there in the first 10,000 terms? Well, finitely many. Finite sets are bounded. So let's just say a few words about why this completes the proof. Well, the set, I'm going to zoom in. The set A1, A2, up through A sub n is finite. Finite sets are bounded, and so is bounded. Let's let U and L be upper slash lower bounds on the set containing the first n elements of the sequence, n terms of the sequence. Sequences don't have elements, they have terms. Then, and I'll be a little bit black boxy, maybe I won't explain it. then the max between u and a sub big N plus 1 is an upper bound on the sequence a sub n, while a sub big N plus 1 minus 1 min comma L is a lower bound. And there is space here to explain why, but maybe I'll say that we've done something like this before when we went and showed that every convergent sequence is bounded. We did the exact same thing, just to repeat the same proof. Since we've established some bounds, thus a sub n is bounded. So this is a bounded sequence. The Bolzano-Weierstrass theorem now says something. By the Bolzano-Weierstrass theorem, a sub n has a, let's lead into the way that the next sentence is actually written, subsequential limit. This is really interesting that like this random stuff is just showing up and I can't erase it. Nice. So this thing has a subsequential limit. Let's let A be that subsequential limit. Let's let A sub n sub k be a subsequence which converges to A, and off to the side, we said what our next step was going to be. If A sub n converges, then it only has one possible target to converge to. If it converged to 5, then every subsequence would converge to 5, but I found a subsequence which converges to A, so 5 must be A. In general, if A sub n converges, it has to converge to that number A. Claim A sub n converges to A. So let's try to do it. That's interesting that how these things moved. I want some more space off to the side now, though. So let's get to this proof. I claim that A sub n converges to A. And I'll do a similar pictorial proof. So there's this, oh, that's no good. There's this alleged limit A. I want to show that for a sufficiently big choice of n, A sub n is within a distance of epsilon of A. And, well, what can I get close to A? Well, I can get A sub n sub k close to A. I can get that distance to be less than epsilon by taking k big enough. Little k bigger than some threshold value, big K. Let's see. There's A sub subscript. There's A sub subscript. As long as little n is bigger than the big N that comes from Cauchy, and n sub k is bigger than the big N that comes from Cauchy, then I can get this to be less than epsilon. So this side can be less than epsilon if little n is bigger than big N, and n sub k is bigger than big N. And now, well, I even know how the proof should be fixed. I need to divide that by 2. I need to divide that by 2. Then I'll get this to be an epsilon. Nice. So I, in some sense, know how the proof will go. It's just a matter of writing it down. Maybe I'll even encourage you to pause right here and complete the rest of the proof on your own. Okay, good. You did that. You completed the proof. So let's do it. I want to show that a thing converges, so let's show that a thing converges. So how will we do that? Well, we need to consider any epsilon and then come up with a threshold value. So let's consider any epsilon bigger than 0. I know that a sub n is Cauchy, so that tells me that there exists some big N such that whenever little m is bigger than big N and little m is bigger than big N, then the difference between a sub n and a sub m is less than epsilon over 2. And I know I need an epsilon over 2 because of the picture that I just drew. The other thing I know is that a sub n sub k converges to a. That tells me that there exists some threshold value, I don't know what it is, big K, such that if little k is bigger than big K, then a sub n sub k minus a in absolute value is less than epsilon over 2. So let's see. If I can arrange that simultaneously little k is bigger than big K and little n sub k is bigger than big N, then I'll be able to get something. If I can get this to be true, then I will conclude that this is true with little m equal to n sub k. And the same choice of little n is right here. If I can have little k be bigger than big K, then I'll get this to be true. So, well, you can arrange that. There exists a choice of little n that is for which k is bigger than big K and n sub k is bigger than big N. If you want to, like, write it out, I bet n equal to the max between big N, k, equal to the max between big N and big K should do the trick. For this choice of little k, and for any choice of little n bigger than big N, I have that a sub n minus a sub n sub k is less than epsilon over 2. That should be black. And that's by this, hence the 2.5. And I have that a sub n sub k minus a in absolute value is less than epsilon over 2 by 2.6. That's this inequality. Adding these together using the triangle inequality, I see that the absolute value of a sub n minus a. Well, right now I know that a sub n and a are both close to a sub n sub k, so I should subtract and add a sub n sub k. There, I did it. The absolute value of a sub n minus a is equal to that, is less than or equal to the absolute value of a sub n minus a sub n sub k plus absolute value a sub n sub k minus a is less than epsilon over 2 plus epsilon over 2 using this and this. And those two things, of course, add up to epsilon. Oh, wait, so what did we just show? Let's write down a concluding sentence to this little claim. Thus, well, let's see, we started by considering any epsilon bigger than 0, and then we came up with a choice of big N. For all epsilon bigger than 0, there exists a choice of big N. I then did some stuff, and eventually considered any little n bigger than big N. And, well, there was also the stuff about k, but that was part of the proof, not part of the conclusion. For all little n bigger than big N, absolute value of a sub n minus a is less than epsilon. So, a sub n converges to a. That's exactly what the claim said. Let's even just read back up and make sure that we've addressed the claim. Yeah. The claim says a sub n converges to a. We just showed that a sub n converges to a. And now let's just conclude the theorem. So we started by considering any Cauchy sequence, and that claim says that A sub n converges to A, where A is a subsequential limit, which existed because A sub n was bounded. But in particular, we just found the limit of an arbitrary Cauchy sequence. Thus, every Cauchy sequence converges. This completes the proof. Excellent.